And Chava, do you also want to announce that we'll
Oh,
be
yeah,
recording,
sure. What?
like announce that we'll be recording the class if anyone has any?
Yes, exactly. So let it be known for everyone who is on the call or who is going to join it later that this class is being recorded. And that means whatever Google wants to record, that is shown on, I don't know, like whatever Google thinks is notable to be recorded is potentially going to stay on the internet forever. Who knows? So be careful. But at the same time, just be yourself. It's like, we want this to be a lighthearted class, not something very kind of strive up because of this recording. Anyways, but that's the notice. So with that, let's get started. So welcome everyone, official and unofficial students and other interested parties. This is going to be my attempt on teaching you some aspects of like how theoreticians think about reinforcement learning and related problems. At the UOA, this is CMPUT 653. I hope that you're at the right place if you're on this call. And the class time is going to be just this time on Tuesdays and Thursdays. And we are going to be all virtual. And so let me say a few words about who am I, and then maybe I want to introduce the whole team, because we have a team now, because it's a big class. So I'm Csaba Szepesvári, and I'm a prof at the U of A, have been here since for a long time by now, it feels, but it also feels quite short actually. So time is kind of funny. And I've been doing reinforcement learning theory since the beginning of my adult life. And along these many years, I learned a lot, and my purpose will be to just share some of the things that I've learned over the years and the way I'm thinking about these problems. And right. During the course, you will probably learn more about me. So for now, this is maybe enough. And we have, as I said, a wonderful team of TAs. Alex, wave your hand. Maybe Google shows you, and Shivam, wave your hand. In no particular order. These are the guys who are gonna help me to run this class smoothly, or however it works. So the online delivery mode is going to mean that they're gonna help me with the questions that you guys might be asking while on the call. So normally I will just like look at my tablet and then scribble there, and then I might not notice some of the questions that pop up. You're asked to mute yourselves. If we are this many, then maybe that's a better way of going about this. And then ask the questions in the chat, and Shivan and Alex dutifully agreed to monitor the chat and answer the questions. Other students can also pop in and answer the questions if there are some easy clarification questions, then just please do that. You can also raise your hand. I may or may not notice that. I will try to pay attention to it. But Alex and Shivam are going to jump in if there is a need for interrupting me, because there are some good questions that should be discussed. And with that, I would want to say that I chose not to pre-record the lectures for the purpose because I like to teach in an interactive fashion. Of course, this format is not going to be the same as the classroom format, but I encourage everyone to, turn on your video if if you wish, and I like to see people as they are thinking or they're making faces like, oh, what is this? And then I know that things are not going that well. So give me feedback. And you will see that my style is to ask a lot of questions. And then you can just type in, and then we'll try to make sense of what's going on. If the typing doesn't work, then maybe we're gonna advance with some other technology. But like for now, let's just try to keep it simple. All right, so that's the way I intend to run the class. So what is this class about? I already told you that I just want to teach about how I do think about theoretical aspects of reinforcement learning. Why do I choose the problems I work on, and like how do I think about this space of problems? And what I think I will try to teach you also notable results that that are known at the time in this field. So there will be some teaching about like what are the questions, then there are like what are the answers if we do have the answers, why do we ask these questions, and then are we happy with the answers that we have, and what is unknown. So we'll try to stay on the forefront of research. So hopefully by the end of the class, you will be able to go in and read papers in the literature that are currently under publication. And you will say, okay, this is how it connects to how everything else was done previously. And so that's kind of my goal with this class. So I will think that I'm successful in teaching you if many of you at the end will feel that you can read these papers and then you can place them in the literature and you can maybe ask similar questions and then maybe answer some of these questions. So having said that, there will be some teaching about the tools and techniques that we use to answer these questions as well. So in addition to just thinking about what are the questions that are worth asking, there are also the questions, okay, how do we answer these questions? So there will be some tools and techniques related to that. So this is kind of my part, and I will try to stay on the top of this. Hopefully you'll like the lectures. We'll have a bunch of homeworks. How many homeworks are we going to have? There will be 4 homeworks. Each is going to worth 10% of the mark, and there will be a take-home midterm that worth 20% of the mark. And new for my type of teaching is that there's going to be a project. And the project is going to worth the rest of the mark, which happens to be 40%, quite a bit. For the assignments and the project, you can work in pairs. I encourage everyone to attempt every problem on their own. For the projects, also you can work alone, or you can discuss with some other person that you chose to work with. You can, like I'm not against like discussing in even bigger groups, and on Slack we are going to have this discussion forum. You can ask questions there. That's all fine. But mainly, I encourage you to work on the individual problems alone, because that's the way you can learn the most, right? Like then you learn like what you're missing, what you get, what you don't get. Even if you like struggling for a while and trying before jumping on and asking those questions, that's what's really makes a big difference. Because maybe, okay, then you get a hint, but then you can go back and then retrospectively ask, okay, what was that I was missing? Why did I miss this? And then you know how to fill your gaps. and you become a better problem solver that way. So that's about the assignments and the project. So the midterm should be done alone. It's a take-home midterm. COVID times anyways. My midterms are usually take-home anyways, and exams as well. Usual academic honesty rules apply. Those shouldn't surprise anyone. We are here for learning. So I try to teach you, I try my best, you try your best to learn, and then we will be a happy family of people learning about reinforcement learning theory. That's the purpose. So for the project, we're gonna have a description of what the projects are about a little bit later in a couple of days on the website. But the intention is that the project is going to be something like it's theory, right? So it's not like that you would be running experiments and writing code and whatnot. You can do that if you want, but it's absolutely not required. And we have different types of projects that you can attempt. So one type could be just you read a paper, you really like it, it's kind of like a theory paper, and then you want to write a critical evaluation of that paper. So where does this fit in the literature? How does it compare to existing results? It's like a commentary. So some statistics journals, NS of Statistics, for example, does have these commentary sections where someone's invited to write a commentary on an article. So that means that the person is the expert in the field, and he's privileged to be invited to write this commentary. So in this class, you're privileged to be invited to write commentaries on other people's papers that you can choose. But the commentary is expected to be, like an expert's opinion. It's not just like regurgitating what the authors are writing, but like your thoughts related to what the authors were writing. So that means that you should know a little bit more about the related literature, and then maybe you should bring some aspects that are perhaps overlooked by the authors to the table, or maybe just the author didn't have space or time to expand on those things. So this is one possible project. Other possible projects are reviewing an area. Other possible projects are just rewriting one paper that you've read, and now you rewrite it and make it nicer. Like the proofs are nicer, shorter, the whole thing is nicer. That's also a very versatile project in my eyes.
I wanted to add for that project, it also may be useful to, like, if you read an RL paper, think about a simpler setting like bandits or something, and then maybe try to extend the results to that setting and think, is this reasonable in this setting or not?
That's right. That's right. So another type of project is trying to transport results from one setting to another. We'll learn about many different settings. And people, when they write their papers, they maybe somewhat arbitrarily choose some setting. And then you can ask the question, but like, does this result hold in this other setting? Like, how would it look like? And sometimes this question is not that hard. And maybe you can even write a research paper about something like this. Sometimes it turns out to be a little bit more challenging. So this is a little bit on the riskier side. So one advice here for the projects is that you can start with a lower risk version of it, like rewriting a paper or writing a commentary on a paper. And then, like one thought follows the other. And then you will try to think, oh, I do have some more time. Like maybe I can add this to this, or I can add that to this. And then you make it a little bit bigger project. So that's about the projects. So you have seen that we already released the zeros homework. which is kind of almost a self-assessment homework, although we're going to mark it, and it's going to be a pass and fail. So you have to achieve a certain percentage. I think it's 85 out of 150 or something, or I don't remember, but like it's there. And if you fail to achieve that, if you achieve that, then it's like, okay, you're in. If you fail to achieve that, then you have to talk to me. And if you don't want to drop the class after failing to achieve this, if you want to stay in a class, then you have to talk to me and convince me that you'll be fine, and this was just a glitch or something like that. The purpose here is not to show off or anything like that. It's just like, these are the type of problems that will typically come up during the course, and this gives you a chance to see how easy or how difficult these type of problems are for you. So that's homework there. Okay. So we went through the homeworks. You will have 2 weeks for all the homeworks, basically. And then we have the project. You can start working on a project right now. It's a little bit difficult if you start not now, but you can start thinking about like things that you like, that you don't like, how would you do it. And we talked about the midterm in terms of that you have to do that alone. So I think that we covered pretty much everything except the tools. So we have a bunch of tools. We have the website, we have eClass, we have this Google Meet, and we have Slack. So what's the relationship between all of this? So eClass is for people officially enrolled. And we're going to make all the announcements through eClass. So make sure that you receive notifications about announcements made on eClass. If you might be tampering with your notification settings in your eClass, and if these settings are not properly set, then there could be delays. Like you get like a notification once a week or never or whatnot. Like make sure that you get notifications in time. The notifications are going to be like, ouch, like we noticed that there is a little problem with this homework. Here's a new version, which may be useful if you're working on that problem already. So you want to see the announcements. And so that's eClass. We're going to use Slack, 2 channels in Slack. There is the private and there is the public discussion channels related to the class. I encourage everyone to use the public one if you wish. There are more people on the public one than on the private one. On the private one, we're only letting people who are officially taking the class. Alex, did you want to say something?
No.
Okay. All right. And the intention with the Slack forums is that there will be lively discussion there related to the class. Depending on how many messages are going to be there, like I try to be on staying on the top, but again, I think that the lion's share of work will be done by Shivam and Alex, and maybe your peers, like you guys, can chat and bring me in if there is something that like really needs my attention. I will try to stay on top, but like if there are hundreds of messages, then maybe I won't be able to do that. Like, so, all right. We also already talked about Google Meet. The website is going to be like after every lecture, or end of the week, we update it with all the videos of the lectures, and the lecture notes are going to be posted there. My intention is to post lecture notes by the end of the week. That covers the material of the week. That's it. I don't know. Does anyone have any questions for this admin trivia part of the course? This is a good chance to see whether the chat is working. Are you guys here? Say yes. Oh, good. All right. Okay, so one last thing. Shivam suggested that maybe, okay, people should be aware that the recorded lectures are going to be on the website and it will be public.
Chaba?
Yes.
Someone asked
Yes.
about letter grades. Like what are
what is the question about the letter grades?
How about final letter grades? I think do we have a grading scale? Is this to be decided? Just some.
Yeah, it's gonna be ad hoc. It's like following standard practices at the uni, with whatever that means. Like if you work hard and you do the problems, you will get an A+. If you can't solve the problems, you will get something worse. But I don't know, like we'll try our best to be fair. We'll have plenty of discussion about these things. You will get feedback a lot of times. I wouldn't really stress about the letter grades if I were you. I mean, like, yeah, maybe I would, but like, don't be too stressed about it. Just like do it for the learning, and you'll be fine. I rarely fail students in graduate classes. Is that reassuring to know? Okay. All right. So let's do some work. Since we are done with the administration part, let's talk about what this class is really about. All right. So we'll have 3 blocks. And each block is approximately 4 weeks, give or take 1 week. Soon my dog is going to bark. Don't be scared. This is her working time. All right. So the 3 blocks are going to be planning, another block is going to be batch learning, and the 3rd block is going to be online learning. And you can see from this beautiful Venn diagram that everything overlaps with everything. And at the heart of it is going to sit MDPs. That is what I want to talk about mostly today. But before that, let's talk a little bit about how these different topics differ from each other. Well, what happened with Colorado? Right. So planning is just a computational question. So there, the problem is to compute efficiently and effectively some action that you want to take in the environment that leads to good policy. So that's computation. It's pure computation. The others have learning in their names. So batch learning is about learning with a batch of data. So that's the closest to supervised learning. So you have a batch of data, and from the batch of data, you want to extract a policy. If you don't know what a policy is, that's okay. I will explain very, very soon, such that this policy is a good policy. And here there is no interaction with the environment. So in that sense, it's like supervised learning, that someone just saved this data set, and given the data, you just want to extract information from it and then come up with some good stuff, the policy. And the online learning is when there is interaction with the environment. And during the course of this interaction with the environment, things happen, you take actions, the environment state changes, and you get rewards. And you get rewarded for good actions, and you get punished for bad actions, and then you want to be rewarded. So the goal here is to collect as much reward. So that's like classic reinforcement learning. So that's like how reinforcement learning was perhaps first proposed. The reason we're talking about all these other aspects of reinforcement learning, because they kind of like come up anyways. So planning comes up when you decide that, okay, I want to build a model of the environment, and I want to use that model to come up with a good action. You have a planning problem. You have to solve that. So even in the learning problems, you have a planning problem sometimes embedded into it. So that's like a core foundational question, like how do we plan efficiently? Well, which models can we plan efficiently with? Which model should I learn? What models should I learn so that I can plan efficiently afterwards? So that's planning. Batch learning comes up because people are too scared to let your algorithm control their systems. So these are like the interactive thing means that like this computer is running, let's say, a country, and then some people are scared to let a computer run a country for, we don't know why, but they're just scared. And that they, rather than letting you do that, they say, oh yeah, man, calm down, many years, we have collected all this data, you just use this and then prove us that you have a better policy than us. Okay, so in batch learning, you don't only want to learn something good, probably you want to prove to these decision makers that you did something well. So that's batch learning, and that's the significance of it. Like a lot of practical applications would require that you do batch learning. I think people would probably mention healthcare, where tampering with patients is like, okay, you do that after you proved that your policies are not that bad. Okay, and then there is the classic interactive learning. So this is kind of the big picture of the class. So we're gonna start with planning. So this is the first block. Then batch learning is the second block, and online learning is the third block. Is there any questions? Good. Let me ask, okay, so how do we do this? Let's try this. Raise your hand if you're familiar with, okay, planning. I will answer the question later. Raise your hand. Okay, like, yeah, like push the button, raise hand. I don't know whether I can see some summary statistics of this.
Yeah. If you go to the participants window, it'll kind of show you.
Cool. Yeah. Okay. All right. So at least 20 people, 20 some. Okay. So raise your hand. Okay. Put your hand down. And raise your hand if you're familiar with batch learning, like you've heard about batch learning before. Silly questions. Okay, good, good. I wish this tool was a little bit better than this, but okay, good. Not bad. I guess like 2 pages, more people. And raise your hand if you're familiar with online learning. Online RL. All right. Good. Raise your hand if you hear me. And you're paying attention. Okay. Okay. Good. So there was a question, how do I define online learning? I'd be very specific about definitions later. Roughly, online learning is when you're interacting with an unknown environment and you're taking these actions to collect as much reward as you can. And so the goal here is you're measured against like how much reward you could have collected and how much you collected. That's online learning. In this respect, there are other variations of online learning that I don't talk about now. Okay. So as I said, MDPs sit in the heart of all these. So what are MDPs? An MDP is, okay. MDP, what does it stand for? It stands for Markov decision process or problem, depending on which community you belong to. And it's just a mathematical model to model an environment where stochastic transitions between states occur that are controlled by an agent or whoever controls the environment. So there are states, there are actions. So these are the primitives that appear in an MDP. There are stochastic transitions. Between states. And then there are rewards. And there is an objective. So states are primitives. So we don't define what states are. In every application, states mean something different, and we should discuss a little bit about what's the meaning of a state. Actions are similarly primitive. So you just have a set of states, you have a set of actions, and then you have these stochastic transitions as a result of using some action between the states. So that kind of means that you have, okay, this set of states, set of actions, and then you have these stochastic transitions. So what does a stochastic transition mean? It means that like no matter what state you are at and then what action you take, there is a distribution over states that is given by the structure of the Markov decision process, so that if you are in state S and you're taking this action, then the next state is distributed according to this distribution, right? And there are many different alternative ways of denoting this distribution. So one of the ways is just to say that, okay, somehow lower index A, and this is a function of S, and this is just a distribution over states. And this is mostly the notation I'm going to use. But sometimes I'm going to switch to some other notation, but you should be notified about that. And then there are rewards. And for the rewards, I like to keep it simple for just to reduce clutter. Yeah. And so I'm just going to assume that for every state action pair, there is a deterministic reward, which is a real number. Maybe it's in 0, 1. If you're lucky, then it's normalized. So capital R, this stands for reals. And there is also an objective function. So essentially what happens is that if you start at some state S naught, you take some action A naught, and then you transition to a next state, S1, not so fast. And then there you take another action A1, and then this continues. Then for every consecutive pairs of states and actions, there is going to be an underlying reward. And you can sum up these rewards. Oh, it's the other way around. I was thinking about something else. So you can sum up these rewards. And this becomes an infinite sum. And then you want to, these are rewards. So you want to maximize these. So you want these to be the largest possible. Well, there are two problems with this. One problem is that maybe this sum is not even defined for some ways of taking the actions. All right, so maybe this sum is not well defined. So an infinite sum may, not exist. Right? Like crazy, +1, -1, +1, -1. What are you doing with this, right? So that could be some problems. So some people would take the averages. Other people would take, other things like discounting. And this is what I'm going to do at the beginning, all right? And then we'll talk about other variations. So just to deal with the fact that the sum may not be defined, and now I'm going to start to assume that maybe these rewards are in the 0-1 interval. To make everything under control, at least in that case, or maybe it's -1, 1, so that my non-convergent example still holds. Right? Even if it's just 0, 1, like maybe it's an infinite sum, although you would be happy to take infinite amount of reward, right? Like, who cares about that? And then we introduce this little discounting, which what it does is that it says that the further away you're in time, the less the reward worse for you. So the discount factor gamma, this is a number between 0 and 1. And it somehow introduces an implicit regularization or whatnot, like that future rewards don't matter that much. We'll later talk about the effective horizon underlying a discounted problem. So that's like really something like 1/1 minus gamma. So after this many terms, or 1/epsilon times this many terms, if the rewards were all bounded in 0, 1, and you truncate this infinite sum after this many terms, then the remainder that you truncated away is going to be small. So put it a little bit more specific. After this many terms, the rest doesn't really matter. So if you care about, whether you're maximizing rewards up to an epsilon accuracy, then effectively this is the horizon that you're shooting for. And so this kind of tries to answer the question of how to set the discount factor. But to tell you the truth, the reason we are studying the discounted problem is mainly because it's somehow interesting, but relatively simple. So the alternative to discounting would be to take averages. If you take averages, then there are all kind of nasty issues, whether the averages are defined, maybe there is some cyclic behavior again, and the averages are not defined, then you have to take Cesare averages. And then I would be here and lecturing you for a whole semester about like how do we even define this problem in a proper way if you started with the average reward case. And what are the different types of MDPs where the average reward works well and doesn't work well. Okay, maybe I'm exaggerating a little bit here, but it's more complex. And the discounting kind of captures a little bit about that. Maybe the future is not that important, a very long future. And as a starting point, it's good enough. In some other cases, though, we're gonna say that gamma is equal to 1, so you're taking an undiscounted problem, in which case we should be careful enough so that everything is well defined. This is not really a problem if the rewards are non-negative, but the rewards could be negative as well, then who knows what happens. Okay, so this addresses one aspect of the problem. And so if you take, a trajectory, which is this infinite sequence of states and actions and states and actions. I come back to you.
Okay.
Let me just finish this. If you take a trajectory like this, then you can assign a return to this trajectory, which is defined like this. Okay. And so this is this infinite sum. And so once you have the return, then you could say, okay, at least this is well defined now. We have discounting. So let's maximize the return. So terminology, this is called the return. There are all these little words that people like to use, and they help if you remember what they are. Otherwise, they could be just in a way. But anyways, we're going to learn a few of these words. So this is a return. The problem with the return is that it doesn't give chance to that the transitions are stochastic. Since the transitions are stochastic, the return in general has a distribution. You start from some state. You could go here or there, and then you can continue here or there. There's a whole distribution over the trajectories that is induced by however you're interacting with the MDP and the MDP itself. And so the return also has a distribution. And then the question is, okay, since it has a distribution, like what do you mean that you want to maximize the return? Like you can't just maximize the return like pointwise or something. So we tend to take the expectation of the return, but then you have to ask like, okay, expectation with respect to what? What is exactly this distribution? And the distribution is going to be the distribution over the trajectories, which is induced the way you're controlling your MDP and the MDP together. The way you're controlling the MDP, the control policy is just called a policy. All right, so that's the policy that appeared there. So maybe I should turn the page. So we're gonna need policies. So there were some questions. So before we go into policies, I should answer the questions. Alex, are there any outstanding questions, or Shivam?
What was epsilon?
Oh, epsilon here. So I was just like briefly touching on that. If you're interested in maximizing an infinite sum like this, infinite discounted sum, up to an epsilon accuracy, then you could truncate this sum after roughly this many terms. And if you are maximizing the truncated sum up to an epsilon accuracy, you're still maximizing the original sum. It's because the truncation and the original sum, the difference between the two, the remainder, is going to be in the range of epsilon. And we're gonna make this more precise later, so don't worry about this at the moment. You just should feel that the discounting, there's this exponential decay, and after t terms, like you can pull out a gamma to the power of t, and that's a small quantity if t is large. How large t should be, so that quantity is small enough. The remainder is summable, so it's at most 1 over 1 minus gamma. So,
and then Andy had a question about like relating horizons with discounting and maybe kind of like how to formulate that idea. I don't know if Andy's question.
It will come up later. Yeah, okay. Like all of these are going to be made formal and into statements when we are going to need something specific. So for now, this is meant to be, you know, like a high level, like conceptual understanding and building up this understanding. Okay. So policies. So we need policies if we want to talk about distributions over trajectories. So policy in general. So if you're in this decision process and you started at this state, you took this action, and then you continued, and then you were at time t-1 or around t-1 at this state, and then took this action, and now you're in state st. And you could use all this information. So this is the history of the process up to stage t. And based on that, just come up with some way of choosing the actions possibly randomly. Okay? So a policy is allowed to randomize. It can choose random actions. I don't know why would you want to randomize. Maybe one day we will discover that randomization is important. Until then, why not? And I don't know why you would want to use the whole history, but maybe you want to use the whole history. So we don't want to lose generality by just assuming from the get-go that you can't use the whole history. Okay? And here we are also very generous because we're saying that the policy can choose the actions based on past states. That means that the state is observed. Okay? So we're talking about control policies where the controller can observe the states. So anyway, so assign a distribution, and so there are various ways of denoting this. Well, this is going to live in this, you know, s times a to the power of t-1 times s. This is the space of histories up to time t. And this space is maybe this calligraphic h of t, and so then you have a distribution over the actions, and I want to use this notation that if you need a distribution over some set x, then I want to denote it by m1 of x. M stands for measures, and 1 is that these are normalized so that the measure of the whole space is just 1. Okay, so that this is the set of probability distributions over x. So here we want a probability distribution array. So a policy then is going to be just, for every time index, running index, you want a map that maps histories to distributions. Okay, so you should be surprised that the state is observed. So we need to talk about that. We should talk about, okay, like, can we even put this probability measures on these sets, like S and A measures on them? So surprising thing, you need some additional structure if you want to talk about measures on arbitrary sets. And that's the subject of measure theory. You can't just do that like arbitrary, at least if you want to believe in the axiom of choice. And let's not get started on that, okay? So let's just say that I want to skip all this, all right? So for this reason, so that put your mind at ease, I'm going to assume that this set S is finite. I learned this trick from Rich. And I want to assume that the action set is also finite. And then people are going to maybe condemn me for this, or they would say that like everything that we do in this class is going to be so limited and whatnot. Maybe in some way, maybe yes, a little bit. You can extend a lot, almost everything that we do for the continuous case, like big sets and whatnot, assuming some kind of regularity that I don't want to talk about, okay? So the only reason I'm making these assumptions is to keep things simple. Then probability distributions are totally trivial. If you have finite sets, what is a probability distribution? It's the same thing as a probability vector. You assign some probability of seeing every element of the set, and that's it, right? It becomes super simple and very, very intuitive. But the results, sometimes we should discuss whether the results extend to certain cases. So, for example, a roboticist might worry about that if I take finite actions, then what happens to my robot arm that has this, I don't know, like torques everywhere. It has this gripper and then like has fingers and whatnot, and everything seems to be continuous. Well, we know that under the hood, everything is maybe discrete in the universe. Well, we don't know, but could be. But okay, that's the realm of the axiom of choice. We're not discussing this. But lo and behold, pretty much everything that we're going to discuss extend, except that sometimes there are computational barriers that you're going to see. And we should pay attention and keep asking me about this. Like, does this extend? Any caveats there? Sometimes small action sets are going to matter. But then often the times, there is little difference between, exponentially large in some quantity of interest that describes the scaling of your problem and continuously many. Like both of them are horribly complex. So anyways, so that's my little rant about why we don't mostly go beyond the finite case, and it's because we want to avoid measure theory.
Chaba?
Yes.
A couple people are now curious on what these regularity properties are, briefly.
Well, first of all, if you want to put measures on sets, then you have some measurable sets, right? Like you have to decide about some sigma algebras. You have to do that then it's up to you. Like you choose some measure sets. That's the minimum. The second, and that's much more problematic, is that the policies themselves, it's not so easy to just say that, oh, anything goes. Any map that maps histories to distributions over actions goes. You have to have the so-called probability kernel there, which means some regularity assumptions, so that you can compose this probability kernel with the probability kernel underlying the MDP, and you get measures. So that's the second, and it becomes really nasty when you start to talk about whether an optimal policy exists and whether it's measurable. And measurable optimal policy exists. Then you may want to assume something like continuity. And now we're talking about topology and whatnot. It becomes really hairy. So you can imagine. It goes on and on and on. And it's a little bit unclear as well why at the outset your policies should necessarily be measurable. It's a weird question to ask, though. It kind of belongs to the realm of discussing whether the axiom of choice makes sense or not. We are getting into the dirty details here. If we wanted to understand this, so I just say, let's just keep everything finite and worry about big finite sets. So the lesson that I learned from Rich is that big finite is maybe capturing, well, I don't know, he didn't put a percentage on that, but like the 80-20% rule definitely applies. So most of your troubles already arise if you have big finite sets. You don't really need to assume more than that. So big finite, that's the name of the game. And by big, you're gonna mean that maybe it doesn't fit the memory of your computer, right? We'll talk about this.
And then I guess the question is, can you always work with a big finite state action state set, do some analysis, take the limit, and then somehow kind of extend it to continuous cases?
That's the hope. It's not necessarily so simple, but the intuition is that if it works for the big finite set, then it should work. Then you made sufficiently many assumptions that it's going to work. Anyways, this is what the focus is going to be, because it just like frees our mind from a lot of the measure theoretical weirdness that would happen otherwise. All right, so the other thing that we should talk about is that the state is somehow sneakily, we started to assume that the state is observed, because we're talking about controlling the system based on knowing what the state is. Just to be able to talk about these distributions. But maybe this is not such a big deal, because this is like, if you want to know the limits of like how well you could control the system to collect so much reward, then you could say that, well, let's look at the really extreme case where maybe the controller can know the state of the system, but this is a non-trivial assumption. And later on, indeed, lo and behold, we're going to talk a lot about when the cases where, like, we can't, even if we knew what the state is, maybe using the state information, because there are so many states, it's just not possible. Somehow you want to compress. Okay. But the justification here for building up the basic theory is that if you want to understand the limits of what you can do with the system, how much reward you could collect, then this is going to put an upper bound on how much reward you could collect. And to build some intuition, to build some basic theory, this is a good enough starting point. All right. So this doesn't mean that in the rest of the semester, we're always just going to deal with cases where we're strongly using that the state is observed and you can act based on the state. In fact, for most of the course, we want to deal with the case when there are so many states that it's just not practically feasible to do this. And so even if you could observe the state, you would throw away state information, abstract the state, and then act based on abstracted states, which is less information. And then you still want to guarantee that you're going to do well. That's kind of the challenge anyways. All right? But for building the foundations for MDPs, we're going to, MDPs, this optimality and everything is with respect to policies that are allowed to access the state. It's a very high bar. High bar. Right? Right. So there were some questions in the chat whether policies can access the history, past states. Yes. So that's the meaning here, that this is the definition of a general policy. So this is what a policy can do. All right. All right. And then there is the obligatory figure, which is that putting everything together. There are many figures actually, and I should make good use of this medium that I have here that I can just draw. So there is the controller or the agent that has a policy pi, and it sends actions, and it receives state information. More generally, it receives other information as well. And this is the MDP that has the transition dynamics in it. And the stochastic transitions happen, and this is what's called closing the loop. It's a closed loop system, because you can see the loop. It's closed, right? So it goes from here, it gets back, and then depending on what happens, you do something else. It's feedback. So the question is, how well can you control the system using feedback when your goal is to collect as much reward as you can? And so the next thing is that, okay, if you fix a policy and you fix an initial state distribution, and you fix an MDP transition structure, you don't need the rest yet. then this puts a distribution over the space of trajectories. So the trajectory space is just S times A to the power of N. So these are, you know, all these tuples, like S, T, A, T, T greater than 0, for all possible values of ST, and AT, where ST is in A, ST is in S, and AT is in A. So all trajectories. And this distribution, I'm going to denote this distribution by, I guess I put nu in the lower index and pi in the upper index. And the probability of a particular sequence of S naught, A naught, S1, A1, and so on and so forth, is going to be defined as mu is a distribution over the states, so it assigns a probability to every state, including S naught. So mu S naught, and then the probability assigned by the policy to action A on the history. That's the empty. Okay, it's the history that starts with S naught. So this is weird. Wow. So literally, if we go back here, we have these policies. So they take a history, that's the first argument, and then it returns a probability distribution. And so what it returns is a vector or whatnot, probability distribution. And so you can take values of that. So here you have S naught. And so that's a probability distribution. So you take its value at A naught. So there's a probability of A naught under the distribution that is selected by the policy, and we should index this by pi naught, because I said that these are indexed by time. And then there is the probability that comes from making a transition in the MDP. And so that's like P of, well, we are at selecting action A naught at state S naught. And we are interested in what probability it assigns to this next state, S1, right? This looks extremely unwieldy. And it continues, right? So now P1, and then you have S0 and A0 and S1, and then A1 times PA1, S1, S2, and then the next term, all the infinitely many terms. I know you might be wondering about, okay, is this even well defined? This is an infinite product. It's always 0, maybe, or whatnot. Like, it's like a lot of numbers are multiplied here. So it happens that this is well defined. And you can prove that by induction on the length of the trajectories, that these are probability distributions if you truncate after t steps. And they remain probability distributions, and the limit is well defined as probability distribution over these infinitely lengthy trajectories. But rather than doing that, I want to simplify the notation a little bit and then move closer to a notation that's more convenient and more common in the literature. So instead of writing this unwidely thing, how about just writing this is the probability of A naught under S naught. And then like you can write either this, sometimes maybe you want to write something like this. These are all acceptable as long as the convention is well defined. And here, this could be pi 1, A1, S naught, A naught, S1. And then maybe I just use the first convention. Then this is PA1 and S1, S2. Fewer parentheses do not hurt. This function notation is okay, nice and uniform, but at the same time can be pretty hard to read. But this is just notation, and then you can also drop the index that we put in there for the policies, because the index is implied by the length of the history. So this puts a distribution over the trajectories, and then this gives us a way of defining values. So the value, I want to use lowercase. The value of a policy when started from some distribution mu, it's just going to be the expected return on the distribution that is induced by the interconnection. So this is called the interconnection of the policy and the MDP, and it's an interconnection in the sense of this figure, which is expressed in terms of like how these probabilities are assigned to the trajectories, right? Should be all intuitive. Like the probabilities just get multiplied. So that means that everything happens independently given a past, which also means that this is kind of like just saying that something like the Markov property holds. And you can talk about the Markov property a little bit later. Anyway, so you get this interconnection, and so you just want to define this as the expected value of the return the lying a random trajectory. And so the return was defined earlier. So what's this expected value? Well, an expected value over this space is just like you take all possible trajectories. I guess I can use, I don't know, G. Oh, look at that. And then there is the probability of these trajectories, and then so this would be, you know, like all well defined and everything if you truncate the trajectories, and then you have to argue that this is still well defined if you don't truncate the trajectories, but still okay. So this is the value. This is called the value of pi in the MDPM. So this, if you collect everything up, so you have all of these guys, the state, the action, the rewards, and the transition structure. Then this defines an MDP. So an MDP in in this sense, is just this mathematical object, which gives you all of these things. If you want. And maybe gamma is part of the MDP definition or not. Okay, so this is the value of policy pi in this in MDP M. And you can see that the MDP is not denoted, but sometimes the MDP is going to be important, and maybe we'll have to index this by the MDP as well. And then once we have this, then we can start to say things like, okay, what happens if I try to maximize? No, I have values. So I can, these are real numbers. So I can think about what happens if I take the best policy, the supremum over all policies, for a started distribution mu. And so that becomes the optimal value that you can assign to a started distribution. And it turns out that it's enough to study the case when these mu distributions concentrate on a single state. So this is like the Kronecker delta or Dirac delta or whatnot. So the delta S prime is just 1 when S equals S prime and 0 otherwise. And in this case, it would be too much to write all of this. So we are just going to write. Maybe the M is, I'm gonna start dropping the M here. So we can just write V pi of S. So that's the value of policy if you start the policy from state S. And homework, figure out the relationship between V pi mu and V pi S. So I said that V pi S is kind of redundant. If you know all the V pi mu is redundant. If you know all the V pi S's, they act like a base. Okay, can you make this formal? Just some thinking exercise.
We have some questions if you have time.
Yeah, just a second, just finishing up. And then V star of S is just the same thing as above. Is the supreme overall policies of V pi of S. All right, questions?
There was an ongoing debate on, you mentioned that a policy should be measurable, and then I guess the question arose, measurable with respect to what? Should it be with respect to an M1 measure?
Yeah, so when we're talking about these policies here, and we would need to talk about the interconnection of the stochastic transition structure underlying an MDP and a policy. The question is whether you can properly define the induced measure, which we were hand-wavingly doing here by just saying, oh, take all these products. And it's not obvious whether this leads to a measure in general, or whether, yeah, like these things even exist. So the question is how you do this, and under what conditions you can prove that things are measurable. I mean, like the resulting structure is measurable. And there the conditions are going to be on the policy. And the so besides that, the policy has to assign a probability measure to each history. So that kind of means that it has to be a probability kernel. So pi t is a probability kernel from ht to m1, by which we mean this map, but this map has to have some properties. And then the property of this map, and I want to introduce this notation more generally. So I was already using this, right? Like if you have a history ht, then you can talk about the probability of an action under that history. Generally, if you have just a measurable structure over A, you can't really talk about necessarily the probability of a single element of that set. Like that should be a measurable set. And maybe even in that case, it's not too sensible to just talk about that. Maybe, you know, like you have the 0-1 interval, and your measure is such that for any point, it takes the value of 0. Any point has a 0 measure. Like a uniform distribution of the 0-1 interval will have this property. You want to talk about the measures of subsets, measurable subsets. So the generalization of this is going to be that you have pi t assigning a probability to some subset of the action set. Okay, so for every measurable subset of the action set, you want pi t to assign a probability. And for any given history, this should be a probability measure. And the other property that's important is that if you fix such a subset, then you can think about the map that maps the histories to these probabilities. So you're changing the history. And it will be important that this function is measurable as a function of the history. Because otherwise, you can't really compose these probability measures. Because you want to talk about the joint measures, and then like the definitions wouldn't work if you didn't do this.
And then there was a question on T is the set of all trajectories, or?
It is.
Okay, cool. And then, yeah, I think that's it.
All right, so we didn't get too far. In the Bandit book, that's available for free. You can read, if you care about these measurability aspects of problems, you can care about, you can read about how to properly set these things up. In, I think, chapters 2 and 3, Stochastic Processes talks about this probability kernels, and the Jonas-Kutulaska theorem, which allows you to construct this probability measure on the trajectory space. Okay, so that is a theorem that allows you to say that this probability measure that's induced jointly by the MDP and a policy, if these policies are defined in terms of this probability kernels, is well defined, and then everything works. Okay, so that's the restriction that you have to impose. And I guess next time I'm going to continue with this. Did we have something really big outstanding? Yeah, we didn't talk much about any examples. So maybe the next time we should start by discussing some examples of like, is this an MDP? Like, well, what do we need to do to make this MDP? Like, you give me some examples, okay? And then I want to just teach you what I call the fundamental theorem of MDPs. Which just says that if you know V star, that's pretty much sufficient to know how to act optimally. Why is that true? You probably have heard about this. This is more like a review, but if you haven't, then even better. Okay?
Just one quick question. I think should have asked this at the beginning of the lecture. Is this class for me if I don't know RL? Like prerequisites never mentioned any prior knowledge of RL.
Yeah, I'm not really using much prior knowledge of RL. I mean, like it does help if you have seen some RL, but if someone's completely uninitiated on RL, like everything should be well defined and you should be able to follow everything.
So this can be a first course in RL if they have the math background.
Yeah, right.
And then we want to spend, oh, people want to meet your dog.
Okay. Good time.
I have a question. For those who are still trying to finalize their schedule, is
Yes.
this course typically offered yearly?
This is the first time I offer this course.
Okay. See.
So I have no idea.
Okay.
I will see how it goes and whether there is demand for it.
Do we maybe want to spend the last 10 minutes after class just for like kind of a mini office hours or?
Sure. I mean, yeah, fine. Like with this, the class is over. Maybe we can stop recording and like if you guys have any more questions, then we can still chat a little bit.